Okay, the last lecture I did had to do with molarity. We're going to do one more lecture, and this lecture is going to have to do with two concepts. Another concentration unit called molality, and the other thing we're going to talk about real quick is how adding or creating a solution, adding something to a substance can actually change the point at which it changes phase. So by adding a substance to a solution, you can elevate the boiling point, and you can depress or lower the freezing point. And we're going to talk about that, but that's what we're going to cover in this little lecture here. So let's go ahead and jump in. So we left off talking about molarity and how that was the most common type of concentration unit that we have in chemistry, and it is. That's how we see most things on a lab shelf. It's going to be in molarity. But there's another concentration unit that we will use specifically for our boiling point, elevation, and freezing point depression equation, and that is the unit of molality. So molarity had a big M, a capital M. Molality is a little m. And it also has to do with number of moles of your solute. However, instead of being over the number of liters of solution, molality is the number of kilograms of solvent. So for molality, you're going to take the number of moles of solute, and you're going to divide that by the number of kilograms of solvent. Did I just say solution? The kilograms of the solvent. Okay, so it's a part to part. Remember I talked about how molarity is a part to whole? You're taking one piece of the solution and dividing it by the whole of the solution. For molality, you're taking one piece of the solution and dividing it by a different piece, right? Or not one part, the solute divided by the solvent. It's a part to part ratio, okay? All right. And yeah, that is just one other type of concentration unit. Obviously, if you're given something in grams, if you're given the kilograms of the solvent, you can figure out the molality of that substance. I am going to go ahead and pull up I'm going to share the screen here, and I'm going to pull up my notes because I do want to show you a couple of things. Okay, so I'm going to scroll down here. We already talked about some of this. Okay, so here we go. It turns out that when a solute is dissolved into a solvent, the freezing point of the solution will always be lower than that of the pure solvent. So by adding a solute to a solvent, you will lower the freezing point. You will also elevate the boiling point. And there is obviously a number that we can quantify by which that amount will be changed, okay? So when you dissolve a solute into a solvent, the resulting solution is always going to have a lower freezing point and a higher boiling point than the solvent would have on its own. And we quantify that using this equation. Delta T equals -I K sub F times M. Now there is that little m, that molality. Delta T is the change in temperature. Okay, so it's not just a final temperature, it's the final temperature minus the initial temperature. The change in temperature will equal -I times K sub F times M. M is the molality. K sub F is the freezing point depression constant. So this number, it doesn't change. It changes per every substance, right? Different substances have different freezing point constants, but it doesn't change for every time you're using that substance, it's the same. And then I is the number of molecules or ions that your solute will divide into as it dissolves. And we'll talk about that more in just a minute. Okay, so let's look at a couple of examples to help understand how I understand I. So sodium chloride is made up of, its chemical formula is NaCl. It will break into two ions, one plus sodium ion and one minus chlorine ion. So its I would be 2, breaks into two things. Let's look at K2S, potassium sulfide. That's going to break into how many ions? Well, how many atoms are there when it dissolves? There will be 2 positive 1 K ions, and there will be 1 S2 sulfide 2 minus ion. So it would have an I of 3. That's how we deal with ionic compounds. We're just going to look at how many ions are present as it dissolves, and that is our I. However, if you have a covalent compound, all nonmetals, I is always 1. Why is that? Because if you remember when we learned on how covalent compounds dissolve, they dissolve 1 molecule at a time, right? So if you have ammonia NH3 and you dissolve ammonia in something, it's going to dissolve by individual NH3 molecules being peeled off of the whole thing. So every time you have a covalent compound, you always have an I of 1, okay? The freezing point depression constant, as I said, it depends completely on the nature of the solvent alone. So it has to do with the nature of the solvent. And then we have a similar equation to adjust for the changes in boiling point. So the boiling point elevation, if a solute is dissolved in a solvent, the boiling point of the solution will be higher than that of the pure solvent. Delta T equals I K sub B M. It's a different constant. So the K for the freezing point of water is different than the K for the boiling point of water, okay? And another thing you might have noticed, back up here, is that our equation here, the I is negative. Now, why is that? Well, when we are lowering the freezing point, right, we are always going to have a temperature that is lower. So we're going to put a negative in there to make sure that the change in temperature is negative, right? It goes down. And obviously for boiling point, we're always elevating it, so we want a positive number there. So that is how freezing point is depressed and boiling point is elevated when you take a solvent and add it to solute and add it to a solvent. Now, one thing to remember, one more thing I want to just touch on real quick. When we are determining the I value, we're going to look at how the solute dissolves and not the solvent. Okay, so let's look at several compounds here. Zinc chloride, if that's missing an E, sodium chloride, ammonia, ammonium, acetic acid, and aluminum nitrate. Each one of these have the chemical formulas listed. Zinc chloride is going to dissolve into 3 ions, Zn2 plus and 2 chlorine minuses. So it would have an I of 3. Sodium chloride is going to break into 2, as we said earlier, it would have an I of 2. Ammonia is covalent. It's going to dissolve 1 molecule at a time. It would have an I of 1. Ammonium, NH4 1 plus. It's an ion, but it is a covalent polyatomic ion, right? It's going to have an I of 1. It will dissolve 1 NH4 plus at a time. What about acetic acid, which is what we find in vinegar? C2H4O2. These are all non-metals, C, H, and O. So it's going to have an I of 1. Finally, what about aluminum nitrate? Interestingly enough, we got to look at, again, what are the ions? So we would have 1 aluminum ion, and we have 3 nitrate ions. So it would have an I of 4. So which one of those, if you put the same amounts of solutes into the same solution, which one would lower or raise the freezing, lower the freezing point or raise the boiling point more? Well, if everything else was the same in that equation, what would drive that number more, have a greater difference, the change in temperature, would be your I. So the one of these that is the biggest I, aluminum nitrate here, is the one that would lower the freezing point and elevate the boiling point the most. So there you go. A little bit of talk about molality and boiling point and freezing point. And that's it for now. All right. Talk to you later. Bye.